Aha. Antimatter is like matter, moving backwards in time. If I take a beam of antimatter and transfer all of its energy to myself, I will, myself, travel into the past. Brilliant! Alice, can you let me into the control room of the anti-proton accelerator? I'm planning to travel into the past.
Dr. Nuts, you sound as crazy as ever. Okay, I'll let you in. Oh, but please, try not to break anything this time. Oh, Dr. Nuts! Oh, no problem at all.
Ha! I am in the right place. Wow! Wow! I am in the right time. Dr. Einstein, I presume.
I do not have a doctorate yet, and I don't like being disturbed at lunchtime when I have time to think. And by the way, that drawing on your chest looks like my grandmother getting out of bed. And who are you anyway?
My name does not matter. And this is not your grandmother.
This is you at age 70. You see, I'm coming from the future, and I am here to try and help you with your thinking.
Absurd. I need no help in thinking. And doubly absurd. You cannot have come from the future.
Well, let me try to convince you. These days, you're thinking about the speed of light, and you will soon figure out what will be called the theory of relativity.
All my friends know I have been thinking about light for years. Someone can have told you that. But relativity, that is kind of catchy.
And you're beginning to think that no matter how fast you move, you cannot move faster than light.
Jawohl. But this means that we have to review our concept of space and time. This is so revolutionary that no one will ever understand it. I shall never get a doctorate my whole life.
Don't worry, I can assure you you'll get much better than that. But let me show you something about relativity.
What on earth is that?
Oh, it's just a 21st century typewriter with incorporated cinematography. Let me show you. A wave in the water passes by. Now the boat tries to catch up with it. If the boat moves faster than the wave, it will eventually catch up.
Oh, that is clear, but with light waves instead of water waves, things are very different.
Indeed. Suppose that instead of a boat floating in water, I have a rocket floating in empty space.
A kind of space vehicle. Interesting idea.
And a light wave just flashes past. The difference is that no matter how fast it moves, the rocket cannot catch up with the light wave. The speed of light is a speed limit. Nothing can travel faster than light.
Jawohl, but the interesting thing is how the pilot would see all this.
It may sound unbelievable, but no matter how fast the rocket goes, the pilot in the rocket always sees light moving at the same speed. Even if he's moving almost at the speed of light, the light moves away from the pilot at the same speed of light. It boggles the mind.
Yeah, exactly. You see, according to my theory, the pilot must always see light moving away at exactly the same speed, independent of his own velocity. But now the 100-mark question. How would you explain the different behavior of water waves and light waves?
Elementary, dear Albert. In water, you can obviously measure the speed of the boat relative to the water. But in my rocket story, the rocket was moving in empty space, in the vacuum. In the vacuum, there is nothing. How could you possibly measure your speed relative to nothing?
It makes, therefore, sense
that if light moves in vacuum, the speed at which it moves, it's always the same, no matter how fast you think you're moving.
It all sounds obvious to me, but to explain it, that is much less obvious.
Oops, Mr. Einstein, you have company today. Discussing your strange ideas?
I do that with everybody, including you, my dear friend. Simplicia, please meet Dr.
Nuts. Dr. Nuts.
Dr. Nuts? Please meet Simplicia, my most intelligent collaborator. We were discussing how to catch up with waves. How would you do that?
Always your elementary questions. Suppose that I am on a moving boat.
Like this?
And the boat is moving at 1 meter per second to the right. Then a wave overtakes the boat at 3 meters a second. Since I'm running after the wave moves away from me at a velocity of 2 meters a second. This is so simplistic. Why do you ask me?
Because I want to know what you mean by velocity.
But this is obvious. 1 meter per second means that you move in space the distance of 1 meter in a time of 1 second.
Aha, and what if I told you that one of the two velocities is the speed of light, called c, 300,000 kilometers per second?
What difference does it make? If I run after the light wave at a velocity of 100,000 kilometers a second, I see the light moving away from me at a velocity of 200,000 kilometers a second.
And what if I told you that no matter how fast you move, you always see light moving at the same speed?
But you must be joking, Mr. Einstein.
Or else you have to change all the rules of the game. You see, velocity is space divided by time. If, no matter what you do, a certain velocity must be fixed, then you have to change either the concept of space or the concept of time.
Indeed, you have to change both.
Space and time are no longer what they used to be.
Precisely. How an object looks like or how a clock ticks depends on your velocity relative to them. Let me illustrate this with my little relativity camera here. This is what this room would look like if I was moving very fast across it.
Mr. Einstein, you look so funny.
That was not that funny.
And this is what time would feel like if I was getting close to the speed of light as I go by the clock.
This is clear. A clock that is moving fast relative to me appears to me to be ticking more slowly than my own clock.
Exactly. And if I had a twin brother who goes traveling very fast around the world for a long time, when he comes back, he would be younger than I. Very funny. I wonder what to call this phenomenon.
The twin paradox. Let me illustrate it.
Suppose you have two twin brothers. One of them is sitting here on Earth, while the other one is orbiting around very fast. The one on Earth is getting older faster than the one in orbit around him.
And this is why it is a paradox. The one who moved away and came back may think he is the one who was still, and it is the other one who is moving around. In that case, it is the other one who should come back younger. So both twins think that the other guy comes back younger. Which one of them is right?
I must admit I've been a bit puzzled about that too.
It will take you to understand this completely until 1916, when you figure out what is called the general theory of relativity.
Really? What is that?
Don't get carried away. Let me just ask you a question. Does this ring a bell?
MC squared. I'll buy that.
By Jupiter, I just figured that one out. You see, in changing the concept of time, I was also forced to change the concept of energy. One consequence is that an object of mass m, even if it's not moving and seems to have no energy at all, actually has an enormous energy, the value of its mass, multiplied by the square of the speed of light. If I knew how to liberate that absolutely gigantic energy, I cannot imagine what the consequences would be.
Some good and some bad consequences. I'm not going to tell you about that now. Let us go back to business. Suppose this is the velocity, and we have a particle whose velocity is equal to 0. Then its energy equals to mc squared. Now, as the velocity increases, the energy is a little bigger, and then a little bigger, and a little bigger, and a little bigger as we increase the velocity. But if we were to go all the way to the speed of light, the energy would increase to infinity. So, in order to accelerate a particle of mass m to the velocity of light, you would need an infinite energy.
Yeah, but I'm getting carried away in this discussion. You know too much, and I don't know how you know it. It is true that as you move faster and faster, I see your time running slower and slower. But you cannot, you said it yourself, travel faster than light. That would require more than infinite energy. There is simply no real energy at which you can travel so that your watch travels backwards in time. That is why you cannot have come from the future. You cannot have come from the future.
This is clear. If I had two identical clocks and I set one of them in motion, it appears to me to run slower than the other one. If I increase its speed more and more, it appears to go slower and slower. Close to the speed of light, it will almost appear to stop. But it cannot go faster than the speed of light and backwards in time. Otherwise, I can go myself back in time. In which case, I will never come into this room today, as I do every day, to tell you how to think about your strange ideas, Mr. Einstein.
What Simplicia is saying is precisely why I cannot believe that you really exist and that you have come from the future. My crazy imagination must have made you up. Mein Gott, that was quite a dream. I have never made so much progress in so little time.
Shoot, it was just a dream.
I told you, you cannot travel to the past.
The equation E is equal mc squared, in which energy is put equal to mass multiplied with the square of the velocity of light. It follows from the special theory of relativity. The equation E is equal mc squared. The equation with mass and energy. The equation in 1932 experiment. The equation